All right, so sorry, we'll just back up for a moment. Forgot to record, but okay. So we have a current hooked up to we have a circuit hooked up to an alternating current power supply. So we close the switch and we want to describe what happens to the current. Now, in general, that's actually extremely complicated because when you close the switch, the current behaves very erratically, something called transients, but those transients die off very quickly. And what we'll get is a nice sinusoidal current in the end. And so if the power supply is driven by a sine function, so here we have a maximum voltage times sine omega t, which we get just by plugging something into a wall. I'm just going to state for now, where we can show later on that this is actually true, but the current is described by this equation. So we have a maximum current times sine omega t minus phi. And we want to be able to describe the current in the circuit. And so what we have to do is find the maximum current, and this phi is called the phase shift. And so, the power supply is what's driving the current, but the current in the circuit and the power supply are not going to be in phase with each other. Like when the voltage is at its maximum value, typically the current is not going to be at its maximum value. It could be, rising up to its maximum value, or maybe it already passed and it's on its way down. Typically, they're going to be out of phase. And that's because of the presence of the inductor and the capacitor. But that's our goal, is to solve these circuits. This is a series. These are all three elements in series. There's more complicated ways we can do this, but we're going to focus on this problem. So our goal is to find the maximum current and the phase shift. But we're going to do this in parts. Today, I want to look at some simpler circuits and introduce this idea of a Phasor diagram. So to start with, let's say we remove the capacitor and the inductor. So we just have a resistor, and using the loop rule, V for the battery, we have voltage drop across the resistor. So using the loop rule, we have V minus IR equals 0. And just solving for the current, that's trivial. So no problem there. And in this case, phi is 0. So in this case, if all we have is a resistor, the current and the power supply are going to be in phase. Like if we're at maximum voltage, for instance, that'll occur when this sine term is equal to 1. Well, if this is equal to 1, then so is this. And so when we have maximum voltage, we'll have maximum current. When we have 0 voltage, that means sine omega t is 0, which means that the current is going to be 0. So these, the current and the power supply are in phase. And so, but again, even though this is trivial, if we just have a resistor in the circuit, we can still use this to introduce this idea of a Phasor diagram. And so what we do is we draw this arrow. That is going to rotate with an angular velocity omega. So like we're driving, the current is described by this sine function. And so let's say this arrow has a length equal to its maximum. Let's draw this here. Let's say theta is the angle that this arrow makes with respect to this horizontal direction. and we'll say the arrow's rotating, so theta is equal to omega t. And yeah, the voltage, the arrow has a magnitude equal to the maximum voltage, and the sign would just be like the here, if this is our XY diagram, the to get like the instantaneous value at any given time, you know, the sine omega t, that would just be this projection onto the y-axis. So again, like say t equals 0, then you know sine of theta is 0, the voltage is 0. Alternatively, let's say we rotate through 90 degrees. So omega t is 90 degrees, or pi over 2 radians. Then sine is 1. So we're just vertical, and we're at maximum voltage. This arrow's rotating, and so yeah, it's going, you know, if we just look at the tip of the arrow, it's going in a circle. So like here, the voltage is a maximum, here it's 0, then it's negative maximum, back to 0. So yeah. And what we can see, we can also draw a phasor diagram for the current, where the current has a maximum value as well, which will typically be different. That'll be the maximum value divided by the resistance. So let's make that smaller. And because the two are perfectly in phase, the phase, you know, these two arrows rotate together. And so, yeah, we're right now these phasor diagrams might not seem terribly useful, but when we talk about what happens if we have, say, an inductor in a circuit or a capacitor, well, they'll become useful down the road. So again, if all we had was resistance, this would be a very simple thing. We wouldn't have to worry about it. So, but one thing that we can say about this, we're going to find something called the reactants. I'm going to write this down. So we use the Greek letter chi, and I put a subscript R. This is the reactance of a resistor, and that's just equal to the resistance. So we can write this as, here, let's see. See where I can write this. The current as a function of time, we have, let's do it this way. We have the peak current, which is V max over R, times sine of just omega t. There's no phi in this case. And so IT is VT over R. So basically we just have Ohm's law here. And yeah, not very interesting yet. But when we talk about, we'll talk about an inductor next, and draw a phasor diagram for that. And we'll see that this idea of writing Ohm's law for an alternating current when we have other elements, that has some use. So it's hard to kind of explain why we're doing this right now when we just have a resistor. So let's talk about something a little more interesting. Let's erase our resistor and just put an inductor in the circuit. So I'm going to erase basically everything here. And let's analyze this circuit. So we're going to use a loop rule. And again, I'm just doing this because it's very practical. I do want to post a video. This professor at MIT said the loop rule in circumstances like this is complete nonsense. And he is actually correct because, yeah, this loop rule really only applies to conservative systems, which we do not have here. But you can use Faraday's law and write this, get the exact same result. So I'm just doing it the way the book does for convenience. But that video is actually interesting to watch, so I'll post a link if you want to see it. But anyways, actually I'm going to get rid of this switch because we're looking at the long time behavior after the transients have died off. So let's do this. So using our loop rule, we have V minus the voltage across the inductor is L di dt, and that equals 0. And so we're assuming a current of this form. And so let's find di dt. So taking the derivative, basically we have Im. Taking derivative of sine will give us a cosine, but then we have to take the derivative of what's inside the parentheses, so that'll bring out an omega. And then we have cosine omega t minus 5. Okay, so we're done there. But I want to rewrite this using a trig identity. One that I don't remember offhand, but we want to convert cosine into sine. So remember, cosine and sine are like the exact same function. Let's see if we can just get it from, I'm going to first do this from a unit circle because I don't remember the formula. But let's try to reason our way through it. And we can prove it using trig identities. But let's start with this. So if we look at a point, let's say this is an angle theta. The cosine is the x coordinate and sine is the y coordinate. You know what? I think a better way than a unit circle. Let's plot. Let's say theta equals omega t minus 5. And so if we plot cosine omega t minus 5, it looks like this. And so in order to turn this into a sine function, we'd have to move it 90 degrees to the right, or pi over 2 radians to the right. Because then if we do that, we would, this point would move over here. So basically then we would have a sine function. If we shift it pi over 2 to the right. And so to do that shift, we would subtract by pi over 2. So what I believe is true, let's say we take cosine of theta minus pi over 2. Yeah, so we shift it to the right, that should just be equal to sine of theta. Like 99% sure that is true. But let's just check it really quickly to be safe. In general, cosine of A minus B is cosine A cosine B plus sine A, ran out of room, times sine of B. Yeah, when you have like cosine A plus B, if it's, say, sorry, I wrote that wrong. If you have A plus B, you have cosine A cosine B minus sine A sine B. But if we replace B with minus B, cosine doesn't care, but sine does. So I think that's the right trig identity. And then here in this case, A is theta, B is pi over 2. So cosine of theta times cosine of pi over 2. So I didn't write down cosine of theta because cosine of pi over 2 is 0. So then we'd have sine of theta times sine of pi over 2, and sine of pi over 2 is 1. So yeah, we can erase that. It checks out according to our trig identities. Okay, so let's now rewrite this. I'll erase the picture just to make room. So we have Im omega, and then we can replace this with sine omega t minus phi. We want to convert it to I should have done this a little differently. We want to convert it to sine. So I want to convert basically, I think we have to go the opposite way. So I'm going to have to check this again. Always check this again. So I believe that these two things are equal to each other. I went the wrong way. So let me check this. Let's write down sine of A plus B. That's sine A cosine of B. I think it's then plus sine B cosine A. Yeah, I think that's right. So now let's check this. So let's say theta, or let's say A is omega t minus phi, and B is pi over 2. So here we have sine A plus B, and that will give us sine A cosine B. Cosine of B is 0, so we can neglect that term. And so sine A plus B, yeah, sine A cosine B, that's just gone because cosine of B is 0. So we have sine of B, which is 1, and then we have cosine of A. So yeah, these two things are equal. These trig functions, I don't, it's so easy to mix them up. I don't try to remember them. Just, knowing the basic identities so you can check them. You try to think your way through them and then check them. But anyways, so let's look at the voltage across the inductor. So it'll be L times this. I'm going to write it in a particular way. L omega Im times sine of omega t minus phi plus pi over 2. And here we have the voltage for the power supply. Let's call that B. Or not B. It's not a battery, it's alternating current. Let's just say power supply. That's Vm sine omega t. And so you can see that these two are definitely offset. Or I mentioned, like here we have a phase shift in general for an RLC circuit. Here we definitely have a phase shift. They're off by pi over 2. The phase shift in this case is minus pi over 2. Wait, let me back up. Make sure we're looking at the current here. How that relates to the power supply. But let's actually draw a phasor diagram, or let's plot these two. Well, the current is given by this. We kind of start with that assumption. And So if we plot the current as a function of time on this phasor diagram, so the phasor diagram here, we have here's our maximum current, and it's rotating counterclockwise. Yeah, we've got that, like we can say theta is equal to omega t minus phi. So again, as time increases, theta increases as well. So actually in this case, because of the phase shift, theta is actually not necessarily, yeah, when t equals 0, so we don't start out here at t equals 0. Theta would actually start out at, this, whatever that phase shift is. But if we plot the voltage now across the inductor, so we have sine omega t, the angle that defines the current phasor, that's just theta, omega t minus phi. But now the voltage across the inductor leads the current by pi over 2. So it's 90 degrees ahead. So like the voltage across the inductor, so like the phasor represents the peak value, that's 90 degrees ahead because we have this, theta plus pi over 2. And so we say the voltage leads the current, which kind of makes sense if you think about it. Like if you apply a voltage across the inductor, that'll drive a current, but it'll take some time for that current to build up because inductors resist changes in current. So if you start out with like no current, you just create a potential difference between the ends. Take some time for the current to catch up. So like these things are rotating around, the voltage is ahead of the current by 90 degrees. Okay, now let's see if we can put this together. Yeah, we'll look at this term in parentheses, L omega. So we have a relation between like the current and the voltage. They're out of phase, but let's just look at the maximum values. So if we look at the maximum value of the voltage, now it'll occur, that'll be L omega times I max. So again, what the maximum voltage will occur when this whole thing, the omega t minus phi plus pi over 2, whenever that sign is equal to 1. And so we're going to define I'll write it over here. The inductive reactants. So it's chi L. Again, that's a Greek letter. So for an inductor, and again, now we kind of have this Ohm's law type thing. So we can say in this case that the voltage across the maximum value is equal to, it's called the reactance, the inductive reactance times the maximum current. So ultimately what we're going to get is the voltage across an element, the maximum value is going to be the reactance times the peak current. Now, we can't say that Ohm's law is valid in this circuit. Like we don't have this relation in general that V is equal to the reactance times current. Here, let me put a big X through this. And this equation is not true because we are looking at just, there's a phase shift between them. So like here, if we set this to be true, the voltage is equal to that. The reactance is just a constant. And oh wait, sorry, the power supply it doesn't have that phase shift, but the current does. And so this kind of Ohm's law, this simple relation between the voltage of the power supply and the current, that doesn't exactly work when you have an inductor. However, if you just look at the peak values, it does. And it would also apply to the RMS values as well. Because, to get from the peak value to the RMS value, you divide by the square root of 2, and you would do that for both of these. And usually, that's all we care about. I mean, these type of oscillating circuits, they could be oscillating very rapidly. You usually don't care what's happening, like on an extremely, like any particular moment in time. Who really cares what's happening? Usually we're interested in more like average values. And so this idea of reactance is very useful. So we can just have like an Ohm's law for alternating currents, but it applies to either peak or RMS values. And for a resistor, it's just Ohm's law exactly. And because the current and power supply are in phase, if all we have is a resistor, then Ohm's law would apply as a function of time as well, but not for an inductor. And of course, the next step is going to be looking at a capacitor by itself. Okay, so let's look at a capacitor now. And we're doing this just one piece at a time, because ultimately we're going to look at the full circuit and see what happens. And that's where these phasor diagrams will be very useful. But let's start over now with a simple circuit with just a capacitor. All right, so apply our loop rule. We have V. Now for the capacitor, the voltage across the capacitor and so to solve for the current, let's solve for Q. So Q would be C times the voltage, which is V max sine omega t. And we want to relate that to this current by, we're going to have to, last time we took a derivative. So here we're going to have to integrate the current. So Q would be the integral of I dt. And so let's integrate the current. So we can take the I max out, and we integrate sine omega t minus phi. And the integral of sine is minus cosine. I'll just write that without really making the subscript clear. So we're integrating with respect to time. So we get a minus sign in front, and then just the integral of sine would be minus cosine. However, we have to divide by omega. So basically what we do is let's divide by omega, and we'll put an omega here. And then if we make a u substitution, say u is omega t minus phi, then du is omega dt. So that becomes du. So we just have like sine of u du, which we do minus cosine of u. So that's why we have to have that omega in the denominator. Okay. So we want to convert this cosine into a sine now. So what do we have to do here? Let's draw this first. So again, we're saying that this is Q is equal to this. So this is a Q max value here, but it's a minus cosine. So it's going to look like this. We want to convert this into a sine function. So it looks like we want to shift left 90 degrees. That would make it a sine function. So again, I'm going to put a question mark here. We'll probably want to check this. Oh wait, yeah, cosine omega t minus phi. We want to convert that to sine omega t minus phi. So yeah, I believe that cosine omega t minus phi. Oh wait, yeah, I'm doing it wrong again. I think we want to go the other way. So let's think. We want to convert. Oh yeah, we have Q here, which is described by this sine function. Trying to think which way we want to shift this to get the like we want to find the reactance for a capacitor to make this Ohm's law rule valid. So let me think about this for a second. I only want to integrate the current. And so, yeah, we have Q, and then we want to relate that to the power supply. So just think of what I'm actually doing here. I didn't put limits of integration in here. That yeah, basically, let's think Ohm's law. We want to relate the voltage and the current. So that's the voltage. And yeah, we have our loop rule. Maybe let me try something a little different here. See if I can get this to work. So yeah, we have V. The loop rule looks good. The voltage across a capacitor. Oh wait, I think yeah, for a capacitor. So yeah, voltage is 1/C times Q. That part's good. So yeah, we want to, let's think in terms of Ohm's law. We want to relate the current power supply and the current. And so we want to get the current by integrating, oh wait, that would be derivative. So let's see, we'd have C, we have omega cosine omega t. And then we could relate that. We know that the current is Im sine omega t minus phi. How do we get that equal to so yeah, we can do this phase shift now. So yeah, we want to figure out phi here. So if we take sine, well, let's plot cosine look like this. So here we have cosine. So sine omega t minus phi. To shift sine into cosine, we'd have to shift it to the left 90 degrees. No, we'd have to shift it to the right 90 degrees. Yeah, so if we take cosine omega t, we shift it right 90 degrees, again, that would then equal sine. So shift it right, we would have to subtract. So this would be pi over 2 then. So phase shift in this case should be pi over 2. And I got confused figuring out which way things are supposed to be going here. And now, so we can draw a phasor diagram for a capacitor. So the power supply we have a maximum value, it's spinning around, and to get the or no, let's say that this is the peak current. And then let's look at the voltage across the capacitor. Yeah, the voltage across the capacitor then would be, that should lag by 90 degrees. So we think about it, say you have a capacitor, you'd have a current first to build up the charge. So if you picture these rotating, it's like first the current leads the capacitance in this case. So the current lags a voltage for an inductor, but it leads for a capacitor. And the phase shift is always 90 degrees for if you have like a simple case, like if you have a capacitor or an inductor, the phase shift is always going to be 90 degrees. It's just like, which way is it going to go? And like, how are you going to relate the voltage across the inductor or the capacitor to the current? And so for the capacitor, it lags, the voltage lags the current by 90 degrees. For an inductor, it led by 90 degrees. And for a resistor, the two are in phase. But these phasor diagrams, that's what we're going to talk about more on Wednesday. Let's get back to this kind of Ohm's law idea. So if we just look at maximum values, those occur when like the sine or cosine terms equal 1. So the maximum current is equal to the maximum voltage times, I'm going to write it as omega c. And to write this in terms of Ohm's law, so like V is equal to I times the reactance. We can see that the capacitive reactance is 1 over omega c. Okay, so that's basically Ohm's law for alternating currents, and very, very useful, even by themselves, if you just have simple circuits like this, because usually you don't care. You have to understand that these equations only apply to the maximum value or the RMS values, but they don't take the phase difference into account. So unless you have a purely resistive circuit, Ohm's law does not apply for alternating currents. But it does, this basic idea works if you just look at the peak values or the RMS values, which is usually what we're interested in anyways. Okay, so we're going to review these phasor diagrams tomorrow, because, or sorry, Wednesday. I'm going to try, tomorrow I have a kind of an easier day. So I'm going to try and pre-record this one. But yeah, on Wednesday or tomorrow, if I can get this video recorded and uploaded, I'll try to do that early tomorrow. And we want to look at this entire circuit. So we want to solve this circuit where we ignore the transients, and after a short time, it'll settle into a nice sinusoidal function, but there will be this phase shift between the power supply and the current that it is driving. So we've got all the pieces we need to put this together, but we'll talk a lot more about these phasor diagrams and then put the whole thing together. So again, our goal is to solve for the peak voltage and the phase shift, or sorry, the peak current and the phase shift, and then we can describe the current as a function of time. Okay, so sorry, it was a long day, and yeah, I'll try to pre-record as much as I can tomorrow so that we can maybe spend more time just going over problems and not trying to derive things when I'm kind of half asleep. But any questions on anything?
Are you going to make a Dropbox for the homework assignments and the last lab?
Oh, yeah, I've got to definitely. So yeah, I'll make those file uploads.
Okay.
I'll do that. Yeah. So I haven't picked a due date for the homework yet. I'm going to put the third homework assignment. And again, I'm working up solutions as well. I think I'm going to aim for them probably being due on Monday, at least the first two. And that way I can post the solutions after they're due. And you'll have a couple days to look over them. And yeah, that lab, I can do that anytime. I'll make that right now before I forget again. So, oh yeah, I'm gonna stop recording.